The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, good. Let us start. So last time we talked about finding the space-time geometry produced by this D-brane. So just based on symmetry, you can write down the metric as the following. Say some function, and then a Minkowski metric. A Minkowski metric for the 3+1 direction, and then the part for the transverse direction, which you have rotation symmetry. So you should think of this D-brane as a point in R6. Then there's a spherical symmetry in R6 around this point, and then there are other 3+1 direction, which is this 3+1 direction. Okay. So when you solve the Einstein equation, then you find this FH. Just to replace, can be solved explicitly by the following form: some other function h by the same function, with h given by and r is a constant, which is given by the following form. So R essentially have the form of some constant, Newton constant, and the times the tension of the D-brane. And then if you have n of them, and then this can also be, if you've written everything in terms of alpha prime, gs and alpha prime, can be written as 4 pi gs and alpha prime squared. Okay? So this R. So this is just like what you normally see in the Schwarzschild metric. It's like G times the mass, except because of the translation symmetry in this 3+1 direction, so we have the tension appear here. So Gn is proportional to, so Newton constant is proportional to Gs squared, and T3 is proportional to 1 over Gs. So this product turns out to be proportional to Gs. Okay, and there's n of them, so there's n here. And on dimensional ground, this is dimension 4, so you have alpha prime squared here. Okay, so again, you can write down everything on dimensional ground, and the only thing is just this 4 pi. You have to be careful. Okay. So this is the full D-brane metric. So this is the full D-brane metric. So now let's understand a little bit of physics of this metric. So try to understand, which give us a deeper understanding of the physics of these D-branes. So first, let's consider various regime of R. Okay. So let's consider, say, first consider R go to infinity. So in R go to infinity, HR just become 1. H just become 1. Okay, and then you just recover a 10-dimensional Minkowski metric. Okay, so this is very easy to understand. You are infinitely away from the D-brane. Of course, you don't feel anything, and so you just recover the 10-dimensional Minkowski space-time. So here is 1. Here is 1. Just is a funny way to write down 10-dimensional Minkowski space-time. So this is just a flat R6 metric. Okay? And now let's not consider R go to infinity, just only R much, much smaller than R, than this capital R. then this function, so again, let me call this f, let me call this h. So for example, did I call them h or g? Yeah, h, yeah. Yeah, so for example, the f, it's a similar thing with g, with h. So the f will be 1 plus, say something of order r to the power 4 divided by r to the power 4. Similar with the h. So now you recognize that this 1 over r4 is precisely long-range Coulomb potential in 6 dimension, okay, in R6, because only transverse direction matters. And in 3 spatial dimension, if you have a point, then you have 1 over r. And in 6 dimension, then you again you go down 2 powers, then you get 1 over r4. So this behavior can simply be understood, say essentially, say as you have some kind of Coulomb potential. Both due to the, say, the conserved, both due to the charge of this part, charge of the brane, and also due to the gravity. Okay, just you have some long-range potential. So now the interesting thing, things become more interesting, is when r become of order r. When r become order r, then this hr start to be significantly different from 1, okay? And then tells you, so this is the when r order r, the differentiation. Yeah, at this range, deformation of space-time metric from these 3 branes becomes significant. Okay, so in other words, this capital R, this constant, essentially signals the distance from the brane where the gravitational effect or becomes strong. Okay, the gravitational effect of the D-brane becomes strong. And in particular, you can check yourself. You can calculate yourself the curvature radius now become of order r, or the curvature itself. Yeah, let me just say the curvature itself become r to the minus 4, r to the minus 2. Okay. So essentially, the r gives you the say a measure of when the gravity becomes strong, or the scale of the curvature. So we solve this metric in the context of the supergravity, in the context of low energy effective series supergravity. So in order for the approximation to work, we said before we wanted the alpha prime times the curvature to be much smaller than 1. So we said last time. So that means we want this to be much smaller than 1, so that the supergravity approximation can be valid. So now if you look at the expression of the r, so this tells you that the GSM must be much greater than 1. Okay. GSM must be much greater than 1. And also, in order to have the string loop correction to be small, we also need GS to be much smaller than 1. So we need GSN to be much greater than 1, but also GS to be much smaller than 1. So in order for the supergravity approximation to work. Okay. So now let's consider. So when we set up the problem, this metric is written that r equal to 0 is the location of the brane. Okay, r equal to 0 is the location of the brane. That will be when we solve this problem. R equal to 0 is the presumed location of the brane. So now what happens? Let's see what happens when we yeah, that's where you put the source. Okay, that's where you put the source. So now let's consider. Now let's ask the question: what happens to the metric if r goes to 0? If we try to approach the brane, okay? Okay, we try to approach brane. So this is very easy to do. So when r becomes much smaller than r to the capital R, when r goes to 0, then in this expression, this term will dominate. Okay? We can forget about the 1, this term will dominate. So in this case, the h will be given by r to the 4, r4. Okay? Then we just plug this into your original metric. Okay, so you plug this back. So when you plug this back, so h is equal to, so h minus 1/2, then just become r squared divided by r squared. Then we still have dt squared plus dx squared. Then plus r squared divided by r squared. So that's this positive 1/2. Then the r squared plus r squared, the omega 5 squared. Okay? But now, something miraculous happened. Something miraculous happened. So let me slightly write this metric in a slightly more explicit way. And I write it. So let me just separate these two terms. Okay. So there are two important things happened. There are two important things happened. Just to give you yeah, let me just do it here. Yeah, let me do it here. Maybe it's good enough. Maybe not be good, just to be safe. So previously, let's just draw the plot like this. So let's call this R6. Okay, just for my purpose. Yeah, let's consider this is the R6. And yeah, forget about what's outside. It just imagine the yeah. There's no outside. Just the whole thing is R6. Okay. And when we start solving this problem, these D-branes are a point in this R6, and then there's some flux coming out of it. Okay, there's some F5 flux coming out of it. So this is the picture.
But the flux is normal to the F6, or the flux is normal to R6, or
no? The flux is normal to the S5 surrounding the point, and just like that. I'm just saying, think about the plane is the whole R6. There's nothing outside the plane.
Okay.
Okay. I want to reserve the things outside the plane for other purpose. And just now think about R6 is the whole thing. This is your whole space. Okay. So if you look at this situation, there are two things. First, there's a source at r equal to 0. You see a data function which is the source of the flux, and this is the source of the mass. Okay, there's some tension there. And another thing is that if you look at S5 around this point, and this 5, when you go to the point, then S5 will become 0 sides. Okay, so around this point, yeah, just in flat space, around the you have if you write in the polar coordinates, so the sides of this S5 surrounding this point become 0 sides when you go to that point. Okay, Yeah. But now if you look at this metric, now actually when you go to the brane, location of the brane, actually you never reach r equal to 0. Actually this S5 now become a constant size. Okay? And also now if you look at this, so there are two things happening. So first this is 1, this is 2. So the first thing is that S5 direction, S5, let me call it S5. Now has a constant radius. Given by this r. So this is the first thing. And the second thing is that because of this dr square over r square structure, so if you write as a proper distance, write it as a dl square. So dl will be the proper distance. Then when you solve this, then you find L is essentially log R, say plus some constant. Then as R goes to 0, the L goes to, when R goes to 0, the L goes to minus infinity. That means that R equal to 0, yeah, let me just write it here. This means R equal to 0 sits at infinite proper distance away. Okay. So for all practical purpose, the brane has disappeared. Okay. So the geometric picture is that when you include this when you include the gravity of this source, so now I have to draw something called the embedding diagram, just to use this extra direction to show the curvature. Okay. So when you approach this point, what do you find? You don't find the point. Actually, you find that there's an infinite throat. And so when you try to go approach this point, and this is the cross section of this throat, which I can not draw, is S5 with a constant radius. And then this throat has an infinite non-distance. Okay. So L and here and have an infinite distance. Okay. So that's what's happening here. And the size of this sphere, of course, is r, of radius r. Of radius r. So in this picture, so when you include the say what we say the back reaction of the D3 branes, essentially the D3 branes themselves have disappeared. The only thing left are this curved geometry and the fluxes. Yeah, they still the fluxes won't go away. So you will still see the S5 flux, the F5 flux through this S5. Okay, so there's still flux through this S5. Okay. And this metric. So this is S5, which completely decoupled from the rest part. So these have a constant radius. So this S5 have decoupled from the rest part. So it's natural just to look at this part. And this is actually AdS5. So let me call it 1. So 1 is just AdS. It's the metric of 5-dimensional anti-de Sitter space-time and times S5. Okay? And the AdS5 have the metric. So let me just copy here. Essentially just this part, r square r minus dt square plus dx square plus r squared, r squared, r squared. Okay, so this is AdS 5. So something magic has happened. When you try to reach the brane, then you find the brane is no longer there, and actually you develop an infinite throat, and this throat is the matrix given by AdS 5 times S5. Okay? And of course, at infinity, you still see a flat space. At infinity, you still see flat Minkowski space. Okay? So now we have to take a little bit conceptual leap. Yes?
So we just basically found the most general solution of GR with the given symmetries given by the brane. Right?
Yeah, with what do we mean by most general? We have a specific D-branes.
Well, so we fixed the symmetry given by the D3 brane, and then...
No, you also fix the D-brane charge and D-brane tension.
Okay, yeah.
No, that uniquely fix everything.
Okay.
Yeah. Yes.
So what is the nature of the source? Originally in D-brane it's like electromagnetic.
Yeah,
but
yeah.
Now it's like a mass.
No, now the mass, even the mass is gone. You only see a curved space-time, and with some fluxes.
But I mean, that is a curvature is the reason for the mass, right?
Yeah, but the mass now is completely gone. It's sitting. It's in some sense sitting at infinite distance away. You can never reach it. And for all practical purpose, if you leave this space-time, you will never see the source. What you will see, what you will observe is just a curved space-time with some fluxes. And these are also perfect solution of the Einstein equation. Yeah, because away from the source is also perfect solution of Einstein equations. Yeah, you have first.
Yeah. So I was just trying to understand. So the point is that, so is this somehow like protecting us from these issues that, I mean, even electromagnetism or even quantum electromagnetism build these issues of like the divergence of kind of going towards a point charge. So is this somehow like getting around that by like making it, go far away, or not really?
Yeah, no, this is not getting around that. This is the solution presents itself. No, we did not dictate this solution. This is a pure mathematics. And we're just trying to interpret this mathematics.
Right, but I'm saying, but it does achieve that. I mean, we
Yeah,
didn't
achieve
ask
that.
for it.
Right. Yeah, just the solution presents itself.
That's crazy. Okay.
Yeah. Yes.
So, ordinary electromagnetic charge wouldn't distort the space like this, but the DC brane well. What about other brane or other like D4, D5?
Yeah. Though something similar will happen, but the story is even more complicated. Yeah. So the D-brane, the metric is simplest. Yeah. For reasons I will mention later. Yeah. Yeah. So the reason I choose D-brane is just because the metric is the simplest one. Other questions?
So the long-range Coulomb potential, that's from the charge of the brane?
Both.
Okay, you can't really separate them, I guess.
Yeah, in principle you can separate and depend on your probe. Yeah, but from the metric, it just from the, in some sense it comes from the from metric. Of course, you should just interpret it as the gravitational part. Yeah, this is just gravitational part.
I have a question. So there you draw the fluxes flowing out of the cylinder or along the cylinder? I guess it's along the cylinder.
No, not along the cylinder. Along the cylinder is the r direction.
Yeah, the flux is...
The flux is in the S5. Just think of a hollow S2. Think of a hollow square. Think of a hollow S2. Then on the S2 you can have magnetic flux.
Yes, and the flux is along the radial direction.
No, there's no radial direction. If you only have a S2, then there's no radial direction. You just only have a S2.
Oh, okay.
And then you can have a flux on that S2.
Yes.
Yeah, something proportional to F theta phi, say in electromagnetism. Yeah, so this would be a magnetic flux in the, thread in the S2.
Oh yes, but you write it like in R6. If you write it in R6, it is along the radius direction.
Yeah, just forget about in this picture, it's like in the radial direction. But once in this picture, and then this become completely decoupled.
I see.
And then you just have separate S5.
I see.
Yeah. Okay. So now we have to do a little bit conceptual leap. It's not too big. Is that now we have two of these three branes. Okay? So in the description 1, you just have a D-brane. You really just have some Dirichlet boundary conditions in flat, say, Minkowski 10-dimensional space-time, and where open strings can end, where open strings leave, say. So in this picture, you specify some plane, some surface in the Minkowski 10 dimension, and so this is R1, R3, say O1 comma 3 if you include the time direction. So you just specify some plane in the space-time, in the 10-dimensional Minkowski space-time, where on this plane you can have open string excitations. Okay. And then this, the system, of course, can also have closed strings. Then this closed string can interact with the brane, can interact with the open strings, etc. So everything is in the flat space. Everything is in the flat space, and you have open string, you have closed string, open string. Even on the brane, the closed string can interact with the brane. The closed string can interact with open string. In particular, for example, you can send a closed string and absorbed by the brane and then decay into open string. It's possible. So this is just corresponding to, say, or you can have two open string collide, then become a closed string, and then jump out of the brane. Yeah, you can have all kinds of these kind of interactions. The key point is that in this description, the only thing you need is the Dirichlet boundary conditions specified on the on some component of your worldsheet fields for the string. Okay. So this is, but now from here we have also found a different second description. Is that we have space-time metric one, which is some curved space-time, then plus F5 flux on F5. Okay? So here there's no D-branes anymore. We just have some curved space-time with some fluxes. So here the only thing leaves is a closed string. So only closed strings. But those closed strings see a curved geometry. Okay, so now I can include all dimensions. Let me just draw just to contrast these two. Let me draw this picture again. So now let's draw a 10-dimensional picture. So this is R, Minkowski 10. Yeah, so this is Minkowski 10. So when you now go to smaller radius R, and then you develop an infinite throat, so this becomes AdS 5 times S5. Okay? Far down the throat. And here, only closed string can propagate. There's no D-brane, but the closed string can add infinity, in AdS 5, so you can have closed strings. Okay. So is this clear?
Well, we have closed strings because in low energy case, since no strings, we only have an effective field.
Yeah, but you can have, but this is the geometry. This provides the geometry. In principle, the excitations will be closed strings. So if you, now you can do string theory in this geometry.
Oh, I see.
Yeah. So now essentially,
Treat it as a target, new target space, and
exactly,
and do new string theory will.
exactly. So we start with the D-brane, and then we solve the geometry due to that D-branes, geometry due to that D-branes, and then now you can quantize the string theory in that new geometry. Then that will describe how things interact with the D-brane. Yeah, but in this picture, there's no D-brane anymore. There's only closed strings. Okay. So we just have yeah. Good. Yes.
What was F5?
F5 is this F5 form of the type 2B string, which this D-brane carry the charge. So this generalized charge I discussed last time. Yeah. Other questions?
But in last class that we know the F5 is from the effective theory.
Yeah.
And the effective theory is from the open string spectrum.
No. F5 is closed string spectrum.
Oh, it's closed string spectrum. So why can we apply string theory twice? I mean, the first time we get a flex,
Yeah.
and then we get a modified target space.
Yeah.
And then we apply string
Right.
theory again.
Yeah. Yeah, you can.
Okay.
Yeah. String theory, you can work with any curved space-time. You can think about propagating a string in a generic curved space-time. Okay.
Because it seems like the second application of string theory is like a higher order correction.
No.
Seems like.
No, this picture, I'm just look at, forget about D-branes, I just look at some charged object. I can look at some charged object in string theory, and that object have some charge, have some mass, then I work out this metric. And the string must be able to live in that, metric. And if I want to work out the property of the string in that metric, I quantize the string in this geometry. I quantize string geometry. So this point of view, just purely to view the D-brane as some charged object in the string theory. You just solve this geometry. Okay? Any other questions? So this is a very important point. So now the key is by consistency A must be equal to B. So these two descriptions must be equivalent. Okay? So this can be generalization as the simple exercise we described earlier, that if you want to describe the interaction between the two D-branes, you can use in two equivalent ways. One is to consider some loops of open strings, which you only need to consider the flat space. Just consider loops of open strings. Or you consider the graviton exchange between the two D-branes. And the graviton exchange between the two D-branes is to view that the other D-brane have already curved your space-time, and the other D-brane living in that curved space-time. So these are precisely the generalization of that equivalence. Okay? Now, we have two descriptions of D-branes which are completely different. This one involving flat space and open and closed string, and this one only involving closed string but in some curved space-time. Okay? And in principle, both descriptions can, in principle, be valid for all value of alpha prime and G string. Okay? So there are two parameters in the string theory, either alpha prime and by all alpha prime, just consider for all energies. Yeah. Okay?
Why? It seems like they're constrained, no?
Yeah. So first, in this picture, there's no restriction on what is the alpha prime or G string. and you just impose the Dirichlet boundary condition. Sure. And when you have a G string, you just need to include the higher loop diagrams, etc. So when we work out this geometry, so this statement is more try to apply to B. In B, when we work out this geometry, and also this that AdS times S phi, we were working using the approximation that the alpha prime should be small and the G string should be small. Yes. But once you have worked out that solution in this regime, in principle, if you are technically powerful enough, you should be able to extend this to general values of G string and alpha prime. It may not be precisely this metric, but with some kind of deformation of that from alpha prime corrections and G string corrections. But you should be able to do that. Yeah, I'm just saying. So that's why I say can in principle. Got it. Okay. So we must have these two descriptions, and these two descriptions can in principle value for all range of the parameters you can be interested in. Okay. And so this is a very surprising statement. This A equal to B, but there's not much to do about it, because this is a complicated thing, and this is also a complicated thing. This is even more complicated, doing string theory on some curved space-time. In particular, say if you consider G string is very small, etc., then maybe you can do something, but then it's not that interesting because on both sides you do some perturbation theory, etc. Yeah, anyway, so. But the remarkable thing, which Martesina realized in 1997, is that you can actually take a limit of this statement. And when you take a limit of this statement, then the statement becomes very interesting. Then you can actually do a lot. Okay? And the limit is the low energy limit. So if you consider the low energy limit, then you derive what is now called AdS CFT correspondence. We will now explain how to do that. Yes?
It seems like this correspondence between A and B only exists in the low energy limit, because here the closed strings traveling in the B spacetime, that spacetime is only the low energy corrections from the D-brane, not the higher excitation. Because we only solved the low energy effective theory.
No, that's this is a good question, but that's what I was trying to say earlier. So we find this metric by working in this regime. But now if I want to go away from this regime, then if I want to go away from this regime, then I have to take into account alpha prime corrections, etc. And this is a complicated process, but in principle I can do that. Yeah, in principle I can do that. So that geometry may get modified, etc., but something in principle I can do. And now, so now it turns out if you consider the low energy limit of this A equal to B, then you can actually derive a very powerful statement. Okay?
Is this actually the low energy limit?
No, this itself is not low energy limit. This is a classical gravity limit.
Oh, what's the difference? What's the difference?
No, I will explain that. No, this is the classical gravity limit.
Okay.
And at least the low energy limit does not involve this. Does not involve. Yeah, I will explain what is low energy limit. Yeah. Any other questions? Good. Okay. So now let's look at the low energy limit. In particular, here I don't do any restriction on the G string. So G string can, in principle, be strong here. I don't impose any constraint on the string coupling now. I only consider low energy. Okay. So low energy limit corresponding to I fix the energy E, some energy, some process I'm interested in, some typical energy I'm interested in. Then I want to take the alpha prime go to 0 limit. Okay? Or you fix the equivalent, you can fix alpha prime, then you take it equal to 0. Okay? Because only the dimensionless product of them matters, and I can describe either way. Okay? So physically, what is more convenient? Normally, mathematically, normally what is more convenient is that we think we fix E and then take alpha prime goes 0, but you can think either way. Okay? So the low energy limit is essentially just the limit alpha prime times E squared goes to 0. That's the dimensionless statement. Okay, so this is the low energy limit. I only consider those physical process with E that which satisfy this regime. Okay? Good? And I'm doing no restriction on the GS. So now let's consider A. What is the low energy limit for A? For A, we know. So A, we have two sectors. We have open string sector, which is live on the D-brane. Then we also have closed string sector, okay, which live outside the brane. For the open string sector, we just recover. So we discussed before, when on the D-brane, when you go to low energy, what do you get?
Super Yang Mills?
Yes. You just recover Yang-Mills series. You just recover super Yang-Mills series. And in this case, let me give you a special name for the D3 brane. It turns out you get the n equal to 4 super Yang-Mills, just a specific super Yang-Mills series in 4 dimensions. And with gauge group UN, okay, because we have considered D-branes and D-branes. And in particular, as we said before, the Yang-Mills coupling is related to the GS. Okay, it's proportional to the GS. And so D3 brane give rise to a 3+1 dimensional field theory. In the 3+1 dimensional field theory, the Yang-Mills coupling is dimensionless. So there's no other dimensional parameter here. So there's only so there's only numerical factor turned out to be 4 pi, which you can work out by explicit calculations. So this is key, because if there's a scale here, then the story is more complicated, because you have to take alpha goes to 0, etc. Okay? So the key is that this is a dimensionless coupling, so they have this simple relation. So in the open string, when you take the low energy limit, you just get a Yang-Mills series at some finite coupling, okay, which is determined by the string coupling constant. But in this series, there's also a closed string sector. In the closed string sector, again, when you take a low energy limit, you get the massless modes. You get graviton, dilaton, etc. But only massless modes, okay? But now there's a very important point. The coupling between the closed and open string are mediated through gravitational effect, okay? So the coupling between the massless, so only massless modes left. So the coupling between the massless, closed, and open string or closed string themselves or closed string themselves those interactions it's always controlled by G Newton. This we know because this is the low energy limit. You have graviton, it's controlled by G Newton. It's gravitational by gravitational interactions. But now the key is that G Newton, in contrast to this Yang-Mills coupling, which is dimensionless, G Newton is dimensional. And G Newton is proportional to G's S squared, alpha prime to the power 4. So that means in the low energy limit, then the dimensionless coupling, then the dimensionless parameter is g to the power, say, 8, because these have dimension 8. So this is a dimension. This will go to 0. Okay? So that actually tells you in the non-energy limit, the interaction between the open and closed string will decouple. Okay? This is our familiar fact that electron, when we talk about electron, you don't have to talk about gravity, because their energy is so low, their gravity is so weak. Okay? And the gravity only becomes strong if their energy becomes big. Okay? It's just because of this. In 3 + 1, we just Gn times E squared, but here we are in 10 dimensions, E to the power 8 doesn't matter. So now that means in the equal to 0 limit, what we find is we find the interacting n-4 super Yang-Mills 3 plus free gravitons. Plus other massless modes, but they all become free because the interaction essentially switch off. Any interaction in this sector, they switch off. In particular, there's no interaction between these two sectors. Okay? So this is what we get on the A picture.
The coupling is actually G Newton E8, Newton times E8.
I'm just saying this is a dimensionless combination of them.
It's the actual coupling.
No, the actual coupling can be 1/2, can be square root of this. It's controlled by the G Newton. The key thing is controlled by G Newton, and G Newton is a dimensionless. It's a dimensional parameter. That's just the key. Yes.
Why can't they interact through gauge bosons or something?
No, the gauge boson interact with themselves. The interaction of the gauge boson with graviton is gravitational. Have to go through G Newton. The gauge boson will interact with themselves is captured by here. So anything involving gravity, involving dimensional couplings, then they will switch off in the low energy limit. Just like we don't have to worry about the gravitational interaction of an electron when we talk about the hydrogen atom.
No, but we know that from CFT course, but how do we see it from here?
No, it's just from here. No, this is just the thing. You can calculate it carefully. You can calculate precisely. Work out the scattering amplitude between the photon and the graviton. Take the low energy limit. You find that scattering goes to 0. You can do that calculation explicitly and take the limit. But this argument tells you that you don't have to do the calculation. It will always work. Okay, so now let's look at picture B. When we take the low energy limit, and now let's go back to this metric. So actually, it's handy. So now let's look at picture B, the low energy limit. Let's look at this metric. So this is a curved space-time. So when we take low energy limit, we have to be careful, because one important thing you always keep in mind when you have a curved space-time, the time depends on where you sit. You have to always specify a reference time, because time is no longer the absolute thing. Okay, because of the local time, etc., you have to specify your time frame. Okay, and so we have to ask, what is this E? In picture A, translate into this picture. In picture A, everything is in Minkowski space-time, and that E is essentially E of for the Minkowski's time at infinity in the picture B. Okay? So in other words, the E, so here, let me just say the curved space-time must be careful to specify what energy we are interested in, what energy we are talking about. Okay? So the energy depends on now your choice of time, or depend on your observer. Okay? But we have to, but in order to compare A with B, we have to translate what is E in A. This is translated into B is defined with respect to the t, this t there, okay? In other words, it's the time at r equal to infinity, okay? So that energy scale is defined with that to that specific time. But now, when we talk about the physics happening in this space-time, for example, we talk about string theory, stringy excitations, or the mass of the string, or etc. You have to refer to the local proper time at whatever place, at whatever place you are talking about your physical process. Okay. So that means. Oh, actually today we are going to 6:30. Oh, yeah, right. So suppose you are at some location R, then the local proper time which I will call tau, local proper time, the tau, then it's related to the time at infinity by this factor. Okay, by this factor, it just this the local observer, you call this your d tau square. So so they relate to this by this factor. So now you can easily convert. Then the local proper energy is related to the energy we are talking about here by h to the power 1/4 e. Okay. Okay. So now it's a very important, when we take the Lagrange limit, we take this e small. But due to the gravitational redshift effect, this e tau does not have to be small. Okay? And so this is the thing will be important here. So when r is much, much greater than r, so when we are sitting around here, then h is 1, okay? Then the limit e square alpha prime goes 0 really just tells you that all massive closed string decouple. Massive closed string decouple. Okay. In particular, the interaction of more closed strings themselves, by the same argument, they also become weaker and weaker when you go to Lagrange limit. So essentially, again, they become free gravitons. Okay. But now let's look at the other regime and R around here. Okay. So now, this is for that. So let's consider R smaller than R, capital R. And then in this regime, we go to this AdS 5 times S5, then H becomes R to the power 4, R4. And now this statement and the E square alpha prime go to 0, translate. Now you have a redshift factor, E tau square. If I translate into E tau, the local energy scale. Okay? In particular, now, let's remember this R square is R4 is given by that. So this can be written E tau square R square 4 pi GSN goes to 0. So now important thing happened. Important thing just happened. Then you find this alpha prime actually canceled with each other. Alpha prime here and alpha prime there, they cancel each other. And here there's nothing alpha prime left. Okay? So when you take this limit, and then this quantity goes to 0. And now E tau can actually be anything as far as R sufficiently small. Okay? So that means for any E tau, you can even have huge energy, local proper energy. You can satisfy the low energy limit if those modes live at R very close to 0. Means that they live on this throat deep enough. So this is very simple. Physically, this is very simple. Because of this curved space effect, because of this curved space effect, there's a huge amount of redshift between here and there, between the local probe time here and there. Very big energy here, viewed from here, can become very, very small. In particular, you go deeper into this throat, the redshift factor is bigger. So no matter how large the energy, if you go deep enough, will always appear within the low energy limit here. Okay? Okay? So that means when you sit deep enough, then actually anything is allowed, including a massive stream mode. Okay? Including massive stream mode. So now we remember when you go to R go to 0, essentially you get this AdS5 times S5. So in I equal to 0, we just get this geometry, which is AdS5 times S5. So now what we find is that in the low energy limit in the B, we get free gravitons at I equal to infinity, and then plus full string theory in AdS5 times S5. Okay? Full string theory in AdS5 times S5. Yeah. And again, the two sectors decouple, because when you take the low energy limit, then those stringent modes have to live very far down in this throat, and then they have low overlap with the graviton and live at infinity. Okay? And they have low overlap with graviton and live at infinity. Yes?
So I'm confused about just the way that you wrote that. So you say so there's free gravitons at R equals infinity, but also full string theory in the rest. But doesn't full string theory include gravitons?
No. Yeah. This is the full. There's some different graviton in AdS5 times S5. I'm saying full string theory in AdS5 times S5. Those are not free Minkowski space graviton. This is Minkowski space graviton. So this is Minkowski space graviton. Things which live here. The nature are very different. Yes.
This full string theory only for closed strings?
Only closed string. There's no open string in this picture. They're only closed strings. Okay.
I think now you want to cancel the free graviton from both sides. But actually, here seems that you separate them into two things like free graviton, full string theory. But
Sorry?
so why do you do an artificial separation?
No, there's no artificial separation. That's what I just explained. Those free graviton live here, and the string theory live infinitely down the throat. Throat in the low energy limit. They are infinite. They essentially as large proper distance you want to separate them, depending on how low energy you want to go.
But there's something like living at finite R, right? That always continuous.
Yeah, I'm just saying when you take the low energy limit, then the separation then become infinite.
Just don't understand why don't you include the graviton
No, they have nothing to do with each other. Geographically, they live. One is in the this side of the galaxy. The other is living on the other side of the galaxy. They have the wave function have low overlap with each other.
Maybe his question is like there could be something live between them.
Yeah, I'm just saying when you take the low energy limit, then the only mode which can survive, other than the massless mode which live around here, just any finite energy mode, they cannot live in this place. Yeah.
Does the string theory on AdS bioside see the flux as well?
Yeah, flux, yeah, with the flux, yeah. Okay. Then these two sectors should decouple. So now we have derived, say from this A equal to B, then we take the low energy limit. So here we have A equal to 4 super Yang-Mills theory plus free graviton. And here you have type 2B string. AdS 5 times S5 plus free graviton. Okay. And the free graviton part is the same. Then you conclude, and they're just free. And the interacting part of both sides, then you just equate them. Then you find A equal to 4 super Yang-Mills theory. With UN, then is equal to type 2B string. AdS 5 times S5. So this was a surprising statement saying A equal to B. But A and B are both, say, complicated objects. Both are complicated objects. But now when we take the low energy limit, and then one side, then you reach something very surprising because on this side there's no gravity. On this side there's no gravity, but this side is a full string theory. So now you equate some field theory with a full string theory. Okay. Yes.
So the super Yang-Mills is living just on the D-brane.
Yeah.
Okay.
Any questions regarding this?
So for example, when FR equals to big R, then this is also a free graviton.
Yeah, yeah. But that's always finite proper distance away. They always finite proper distance. So the key is that when you talk about the general modes, you can anything you talk about is finite distance away. If we are taking a limit here, then this throat is going to infinity. You are leaving infinite down the throat.
So anything finite is free.
Yeah, anything. When you talk about the finite energy, then the story is always complicated. And then all this geometry will matter. And the thing only becomes simple. You really take the E goes to 0 limit. And it's the same thing here. Same thing in this picture. When we say you go to the incompatible super Yamil theory, you always have to take that limit. E goes to 0 limit, then you completely decouple the other things. Because any tiny non-zero E, there's always some gravity left. So you really have to take that energy go to 0 limit, and then you rescale the energy to be finite. You understand what I mean? You always have to take that singular limit. It's just like when you take in the thermodynamics, you have to take the infinite volume limit, and then things become simple. And here it's the same thing. Yeah. Whenever you have some finite energy, there always of course, some coupling between them. Good. So do you want to have a break? Yeah. This is like a physicist's guess that somehow these two must be the same. Okay. These two must be the same. So this is a surprising statement because because on the one side it's a field theory, and on the other side is a full gravity theory.
So you said that in principle you can generalize this distribution for any metric in the full string theory for any routine.
Yeah.
But in that case, maybe you will probably not get geometry same as AdS 5.
Oh yeah, that's a very good question. That's a very good question. It turns out, indeed logically you may not. But actually, AdS 5 times S 5 is a highly, as I will explain, it's a very highly symmetric space. It turns out actually it is an exact string theory. At least we believe it's an exact string theory geometry. And when you include all those corrections, this will not change. Yeah. Yes.
So with this in mind, that means that people they only know this heuristically.
Yeah.
Okay, so there's no actual proof of this, besides the fact that everyone believes it works.
Yeah, depend on what you the level. What do you mean?
It works.
So the physicist's way it works is that 1 works, 2 works. Yeah, n equal to 1 works, n equal to 2 works, n equal to 3 works, n equal to 4 works. Then we say it works. and this have way past that. So maybe this worked to n to the 10,000, something like that. But it's not the proof.
Sure.
Yeah, but it worked n to the 10,000, something like that. Yeah. Okay, good. So now let's talk about this duality. So this is normally called AdS CFT duality. Okay. So to understand this duality, let's first understand the object in this relation. Okay. So let me just say a little bit about the object in this relation. First, let me say a little bit about anti-de Sitter space. Since the since that may not be something you have worked before. Okay. So one way to write the metric is this metric. So this is AdS 5. So this is AdS 5. Okay. So this is AdS 5 metric. You can actually write it as AdS. Yeah, let me just copy it down. So you can generalize to any number of dimensions. You can generalize to any number of dimensions. If you make this part into a d-dimensional Minkowski space-time, okay, and then this would be the metric of AdS, say d plus 1 dimension. So this is a d plus 1 dimension Minkowski. Then you have another r direction. So let me call this my. So now let me relabel this to be 1. Okay. So R can be considered as a curvature radius of this space-time. So this R is a constant. And this radius R goes from 0 to infinity. Okay? R goes 0 from infinity. So roughly, a geometric picture here is that, so you can see that you have a half space. Okay, you have a half space, R from 0 to infinity. And at each value of R, there's a Minkowski space-time. There's a d-dimensional Minkowski space-time. So if you fix R, then you just get some d-dimensional Minkowski space-time, and with some prefactor to define the scale of that Minkowski space-time. Okay, so just like this, you have a half line R from 0 to infinity. Then at each point of this half line is foliated by a d-dimensional Minkowski space-time. So that's essentially what this does. So the key thing is that the Minkowski time is what we normally call the warped. Is that the scale factor of this Minkowski space-time depends on where you sit in the radial direction. Okay, so this R we normally call radial direction. Depends on where you sit in the radial direction. So when you R goes to infinity, at R goes to infinity, the scale size become infinite. So this we normally call it to be the boundary. So this we call to be the boundary. Say I equal to infinity, we call to be the boundary of the space-time. So this is similar to say when we write the Euclidean metric in this form. When R goes to infinity, the sphere size becomes infinite, and then this is essentially the space-time boundary roughly, and so this can be similarly understood that way. Okay. So this AdS is a space-time. AdS is a space-time of constant curvature, constant negative curvature. Okay. In fact, this is the most symmetric space-time of lective constant curvature. So you can easily check. This satisfies the Einstein equation with the lective cosmological constant. So you can easily check it satisfies the Einstein equation. So now because now I'm using this R denote this radius, this curvature radius. So now I will call my curvature tensor always using the script now. So also Mn now refers to all directions in this AdS. So you can easily check it satisfies this Einstein equation with some cosmological constant. And you can just compute it's easy to compute the curvature of this guy. So let me just write down the answer. So first you can you can compute the curvature of this guy. You can just find the answer. You find that the curvature, the rich scalar, is given by minus d times d plus 1 r squared. Okay. So this is a rich scalar. This r is the same as this is r. And similarly, you find the cosmological constant. Then you can find here from is given by minus 1/2 d minus 1 divided by r squared. Sorry, here should be minus 2. Okay. And I said that this is the most symmetric, homogeneous negative curvature space-time. So this is reflected in that actually you can write the Riemann tensor. The Riemann tensor of this space-time purely in terms of this metric itself without using derivative. Okay, so this is essentially the definition of the most symmetric negative curvature space-time. Is that the Riemann tensor can be written solely in terms of metric itself. Okay. So these are just some facts of this space. So we often use a lot of coordinates. Sometimes it's often convenient to use, instead of using this r, we will introduce another coordinate. We introduce a z equal to r squared divided by capital R squared divided by small r, essentially just the 1 over r. And because the capital R goes from 0 to infinity, then small z also goes from 0 to infinity. But now the boundary, but now z equal to 0 is the boundary. Rather than z equal to infinity. And then the metric can be written in a slightly different way in terms of these z coordinates. You can write in this form, okay? That you can see it easily. So again, here, you just change the label r by z, and now z equal to 0 is the boundary. And going to interior corresponds to increase z. So z corresponding to in the different direction. Okay?
Previously, in order to derive this AdS metric, we already assumed the small r approach to 0.
Yeah.
But here it tends to infinity.
Yeah. That's a very good question. I'm waiting for some of you to ask. So this is the the physicist magic which we described. Yeah, this is the physicist magic. So yeah, let me just say it this way. So you have infinite throat. So we going to low energy limit, we should just go very much down in the throat, okay? But once you go down once you decouple those discrete freedom, then you can just rescale your energy scale, whatever you want. You go to finite energy, etc. And as far as you are in the AdS 5. Once you decouple those things, then you are living in AdS. Then you are living in the AdS, and then you can talk about the energy scale or any radius as you want. Just become relative to itself. You see what I mean?
Is that kind of normalization?
No, this is not normalization. This is just say normally when we take the low energy limit, the reason we take the low energy limit is we want to decouple those massive modes. And once we decouple those massive modes, and then we consider the finite energy. And when consider the finite energy, because we consider finite energy relative to the low, we still consider a finite range of energy. It's the same thing as that. Is this clear to everybody? This is a very important point. Yeah. Good. Yeah? The question is that previously, in order to decouple those high energy modes, when we take the low energy limit, we have to take r equal to 0. So why here we worry about r go to infinity, r equal to infinity here? Okay? Why are we worried about r equal to infinity? It seems like this is going outside our previous regime. But the answer is that once we decouple those high energy modes, then you can just extend the energy to whatever energy range you want, because you have served the purpose of decouple those Yeah, because those things already went to infinity. Don't have to worry about them. Yeah, is it clear? Yeah. Just like in the Yang-Mills theory, we say we take the low energy limit to decouple those massive modes. But eventually, in the Yang-Mills theory, we will consider very high energy process in the Yang-Mills theory. Okay, but those things we decouple have even higher energy scale. Okay. Good. So we call this is this is 1, this is 2. So in fact, actually 1 and 2, they are not covering the full anti-de Sitter space-time. So actually, they only cover a part of anti-de Sitter space-time. So they only cover, say, what is so-called a Poincare patch, a patch of de Sitter space-time, anti-de Sitter space-time. So now let me just mention a little bit what is normally called the global AdS. Okay. So the AdS or global AdS. So yeah, so let me first write down the sentence. So 1 and 2, 1 or 2, only covers a part of full AdS. Okay. So the global AdS, the so-called global AdS, can be defined, can be described as a hyperboloid in the Lorentz space-time. Okay. Hyperboloid in Minkowski, in D plus 2, the Minkowski space-time of signature 2 comma D. Okay. So to make this precise, say for example, if you go to the GR book, for example, the book by Hawking and AdS, called the large-scale structural space-time, the way they define the anti-de Sitter is as follows. So you consider a D plus 2-dimensional Minkowski space-time with signature 2 comma D. So you consider a Minkowski space-time like this. Okay, so now you have D positive signature and 2 negative signature. So X starts from -1 index to 0, which gives you the negative signature, and then you have so this is a Minkowski space-time of the 2 comma D signature. So now you consider the following hypersurface in that space-time. Okay. So this is a hyperboloid in that space-time, and this defines your AdS. Okay. So this surface defines AdS. Okay. This surface defines AdS. So of course, this is a very different way to parameterize parameterize AdS than either this metric or that metric. And you can actually parameterize AdS in many different ways. So now let me just mention a few ways to a few choice of different coordinates to parameterize these hyperboloids. Okay. So the first is what one is called the Poincare coordinates. It's this one. So first is what we call the Poincare coordinates. So in this Poincare coordinates, you introduce r. So r there is given by x minus 1 plus xd. So you take the one of the negative signature and the one of the positive signature. You take x minus 1, xd, you add them together. So this is like some kind of night cone. And then you write x mu. So there we always write x mu equal to tx. Okay, so this is a d-dimensional Minkowski coordinate. You add x mu equal to r times capital mu divided by r. Okay. So in this hyperboloid, you make this definition, and then you restrict to the region of r greater than 0. Then you recover. So 1 corresponds to r greater than 0 part of this metric, okay, of this space-time. And you can easily check yourself. Just make this definition. This is the exercise you should do, which I don't have time to do here. Just plug this in, plug this into that metric, plug this parameterization into that metric, and then you find you will recover 1. And 1 will correspond. 1 is only restricted to r equal to 0 to infinity, so you only restrict to the r greater than 0 part of this. And if you just introduce this in principle, of course, r can be smaller than 0. Okay. So this is Poincare coordinates. So once you go to that metric, then go to this metric. Just it's the same. Then also let me describe something called the global coordinates. So this is by notice the following structure. So this is have the form of the two, the difference of two squares. So I can write. So let's write x I to 1 to d xi square to be some function r square and r square times r square. So this r have nothing to do with that r now. Now we are doing a different set of coordinates. I'm just using the same notation for convenience. So let's introduce a new coordinate r, which is just the sum of all these square. And then I introduce, then from this equation, the x1 minus x0 square should be equal to r square plus 1 times r square. Okay? So now I can, so this is a circle. So for fixed r, this is a circle. For fixed r, this is a d minus 1 dimensional sphere. Okay? So I can introduce the d minus 1 spherical coordinates on this, and introduce a circular coordinate on this. Okay? So if I do that, so let me just call the circular coordinate down here tau, the polar coordinate in the x minus y, polar coordinate in the x minus 1 and x0 plane. So let me call this tau, and let me call the a spherical coordinate here omega minus 1, omega d minus 1. Okay? Then you plug this into here. Then you find the following metric. So you find the following metric. You find ds square equal to r square minus 1 plus r square d tau square plus dr square plus 1 plus r square plus r square d omega d minus 1 square. So remember, tau is the polar coordinate in this x minus 1 and x0 plane, and omega d minus 1 is the polar coordinate in the x1 to xt. Okay? And then you get this. Again, it's an exercise you should go through yourself. Yes?
So one question, so I'm just trying to visualize this. So there's these, I mean, at least the way it works in RM, I imagine. So you have these two sheets which are like disjoint from each other.
Right.
So how is it that this enables us to go smoothly between them? Like it seems that there's, so maybe I'm confused about what you did.
Sure, what do you mean?
So we're trying to describe this object which has two disjoint components.
We only look at one component.
So what's the point of global coordinates? Is it just a different?
No, that only covers part of the one component.
Oh, I see. Okay. Yes.
Yeah. Yeah. Okay, good. So you look at here. Yeah. So that's the again R, where it goes from 0 to infinity, but this R is very different from this R now. Okay. So in this definition, tau is a polar coordinate. So in this definition, tau will go from 0 to 2 pi, okay? But once you write it in this form, nothing depends on tau, so you can extend tau to any range you want. So once we write this form, we take tau, goes to minus infinity to plus infinity. So this is our generating time, rather than from 0 to 2 pi, we take tau from minus infinity to plus infinity. So sometimes this is also called extended AdS. Sometimes people don't just bother to do that. You just extend it automatically. Okay. So strictly speaking, this, as a definition of AdS, only corresponding to the part of tau from 0 to 2 pi. Okay. And when you extend tau from minus infinity to plus infinity, you actually have an infinite copy of this. Okay, so now with one more thing, we can. So this coordinate is nice. Now it covers everything. Covers everything, but even actually a little bit more, because you have now you extend the tau to minus infinity to infinity. We can visualize this metric a little bit better by doing the following a lot of transformation. So now let's take. Yeah. Before so that, let me say a few words about. Yeah, let me just do this first. So let's take tau again. Take r equal to tangent rho some other coordinates. And r from 0 to infinity, then rho would be from 0 to 2 pi, pi over 2. Okay? 0 pi over 2. And you plug this into here with a little bit tiny. So after 2 seconds, you find the following metric. Okay. So this is easy to see, because 1 plus tangent rho square is just 1 over cosine square, and etc. So the reason this metric is nice, because other than this conformal factor, this thing we can easily recognize. So this is just a cylinder. So this is just a cylinder. And let me draw it here. So this is a cylinder. Okay. So this direction can be considered the radial direction is the rho direction. And the circular direction, and this direction is the tau direction. And this direction is the omega d minus 1, all the polar coordinate direction. I'm only drawing one of them. Okay. So essentially, this have a structure of a cylinder. And at the center here, I have rho equal to 0. And here, I have rho equal to pi over 2. Okay? To go rho from 0 to pi over 2. Okay? And when you go to pi over 2, this cosine factor goes to 0. So the overall scale blows up. So here is your boundary. So pi over 2. Yeah. So pi over 2 is the boundary. Okay. Is this clear? So pi over 2 is the boundary. Now the boundary map. So the boundary of the cylinder. So the boundary now is sitting at rho equal to pi over 2. Has the topology of R times SD minus 1. Okay? So the boundary itself is a cylinder. So the boundary itself is a cylinder. The whole space is a solid cylinder. It's a field cylinder. Okay? But the scale factor blows up when you approach the boundary because of this prefactor. And the R is the time, and the SD minus 1 is the. So let's now, to visualize this space a little bit more better, let's look at the cross section. So imagine you put a plane in this space, okay? So now imagine, now let me call this this circular direction, let's call it theta. And then now let's consider the cross section across this solid cylinder. So then we just have a plane. Okay? Have a plane. I should not have. Let's consider this cross section. Okay? In the center of this cylinder, cut half. Cylinder cut it in half. So for example, in this notation, so this will be rho equal to 0. So here is rho equal to pi over 2. And I introduce this angular coordinate, so that will correspond to theta equal to 0. And here will be, again, rho equal to pi over 2, but theta equal to pi. Okay? And again, this is the tau direction. Is it clear what I'm doing? So I cut the cylinder in half, and that's that cross section. So now, because of this structure of this times a conformal factor overall, a scale factor, so the propagation of a light ray does not depend on this overall factor. The propagation of light ray can be seen from here. Okay? So now let's consider radial light ray, which only goes into the rho direction. Say so there's no in this angular direction. Let's consider the radial light ray. Then from that picture, it's very clear. So let's say this is tau equal to 0. Then it actually takes only pi over 2 for light ray to reach the boundary. Okay, because the rho only goes from pi over 2, and light ray always travel in 45 degrees. So this is just like, if you look at d minus tau plus d rho squared, this is just Minkowski. And so light ray travel 45 degree. And then you reach the boundary, and then take another pi over 2. Yeah, so this is pi over 2. So this is tau equal to 0, and then this will be tau equal to pi over 2. Then suppose you put some reflecting wall here. Then by the time tau equal to pi, it has bounced back. Okay? And now if you go another round, then after at tau equal to 2 pi, then precisely go back to the origin. Then you go through a period, okay? And that actually precisely is that the tau equal to 2 pi, which you define the angular coordinates. Yeah, if you follow that, then that corresponds to precisely 1 period of the light ray traveling in this thing, okay? But the key thing is that the light ray will travel pi over 2 to the boundary. And now you can check, if you look at not the light ray, so light ray travels along the light-like geodesics, but if you look at the time-like geodesic, which is traveled by a massive particle, then you can show that the massive particle never reach the boundary. It will go into a motion like this. Okay, so this is a massive particle. So the massive particle will never reach the boundary. Will always be reflected back intuitively from the gravity potential. Okay, so you will show this fact yourself in your p-set to show that actually the massive particle will never reach the boundary. So in the sense, so if you look at this metric at rho equal to 0, at rho equal to 0, this is essentially like a flat metric, because at rho equal to 0, this is just a sphere. So this becomes 1. This is a sphere. Yeah, rho equal to 0. This is just like a Euclidean space, because this sine rho square becomes rho square. Okay, so this just becomes like a Euclidean space in polar coordinates. And then you have a time, and then this scale factor becomes 1. So at rho equal to 0, just like you have ordinary Minkowski space-time, and then the curvature comes in when you go to finite rho, and then those factors become important. And then you can show, just because of that, you can show that the massive particle will never actually travel to the boundary. Okay, always reflected back. In some sense, you can think of that the massive particle is always pulled back by the gravitational potential. Okay, pulled back by gravitational potential. So from a different point of view, is that another way to say it is a familiar statement which people often make, and often can give you great intuition, physical intuition, in many physical problems. Is that AdS is like a confining box. Just like a box. So things cannot escape from it. Okay? Okay? And in particular, the typical curvature radius is r. So you can roughly imagine this, because in the center it's like a flat space. So it's more like a box of size r. Okay, it's roughly, you can heuristic think of it as a box of size r.
Yes. Does it have finite or infinite volume? Does it have finite or infinite volume?
Yeah, it has infinite volume.
It's infinite volume. Yeah.
Yeah, but because it's confining, most of the particles will only see the size r.
So one other question. So is it correct to say that it's like an anti-harmonic trap? If I'm in the space and I throw a ball out, it's going to come and hit me back in the head or something like that? Like, it seems like
right. Yeah, it'll bounce back. Yeah. Actually, our own friend, Frank Wilczek, in the 80s, have tried to use this AdS, this feature, to say maybe this actually it describes confinement, because if you put a quark there, then they're confined. Anyway. Yeah, but keep this heuristic picture in mind, because many physical problems actually, if you think of, in terms of this picture, become very intuitive. Okay. Okay. And often, so you say this is an exception for the light ray, but often we impose the reflecting boundary condition on the light ray, and for the light ray, this is also like a box. And you go to the boundary and you bounce back, etc. Okay. So now let me again just say it, but you should go back to check yourself. Now by looking at the relation between here, so here is a specific relation between R and X. And here is a specific relation between this X and this tau and this R. You can find the relation between this Poincare coordinate and this global coordinate. Okay, use a little bit of effort. And then you can show yourself. Let me just draw the picture. Again, let me use in the same picture. You can show that the Poincare patch cover a wedge, say at least in this cross section. The Poincare patch cover a cross section of this global AdS. Okay, so here is tau equal to minus pi, and here is tau equal to plus pi, and here say tau equal to 0. And in this Poincare patch, and then this line become R equal to 0, and T equal to minus infinity, and this line become R equal to 0, and T plus infinity. Okay, T plus infinity. And so the time essentially goes around like this. Time goes around like this, and this line corresponding to T equal to 0. Okay, so T equal to 0 and tau equal to 0 coincides, and then you go to minus infinity rotating to that. So and the constant R surface. So this is a constant R surface in the Poincare coordinates. Goes like this, so the time goes up. Okay, and you can check yourself just by working out the relation between those coordinates through the X.
You mean this is wrapped on the cylinder?
No. I'm just saying.
Which picture? This is this picture.
Just within this cross section, I can look at this cross section. I see how this translates into Poincare coordinates, and that's what's happening. A Poincare coordinate cover this part. Okay. Okay, cover this part. I can also draw a more fancy picture here. Then roughly, what you can show is that in this general picture, is that the Poincare patch covers something like this. Okay, and the region between these two lines. So this is a spatial infinity of the in this Poincare patch. The boundary is Minkowski spacetime. So you see, so the Poincare patch cover like that, and then this is a spatial infinity of the Minkowski spacetime. This is the time infinity and time path of the Minkowski spacetime. Okay, so I urge you to do it yourself, because this kind of thing you really have to work through yourself to have intuitive feeling for it. But this is a picture. Once you work out yourself, you compare with my picture, and then you will understand. Okay. So I will stop here today. So in some sense, yeah. Let me just say one more sentence. This extended AdS contains infinite copies of this Poincare patch. Okay.